So in one of the other videos, I talked about Boyce-Codd normal form, or BCNF, as a suitable way of decomposing a schema to minimise redundancy. Now, BCNF has one particular problem, that having decomposed the schema, some of the functional dependencies that are inherent in the schema may no longer exist. I mean, conceptually they exist, but you may have taken the attributes from either side of the functional dependency and they might have ended up in separate tables. That's a problem. So that dependency is no longer relevant to that schema, if you like. So if you want to preserve all the functional dependencies, there's another normal form called third normal form, or most commonly called 3NF. Now, third normal form is slightly weaker than Boyce-Codd normal form, and basically the definition is, so you've got, for all of your functional dependencies, like that. Remember that X and Y are sets of attributes. Either there are is trivial, so we've got something like B determines B, in which case we can basically ignore it. And the second condition, which is the important one for BCNF, was that the left-hand side has to be, the normal phrasing of the definition is has to be part of a superkey, but let's just say that it basically has to be a key. Now, 3NF actually weakens that and allows you to have one more kind of possibility, that all of the, even if X isn't a key, then all of the attributes in Y are part of a key. So there are clearly some third normal form schemas that satisfy these that don't satisfy BCNF. Okay, so that's the essential difference between 3NF and BCNF is that third test there. So clearly schemas that satisfy 1 and 2 are in BCNF, and they're also in 3NF, but there are schemas that satisfy the first two but don't satisfy the first one, don't satisfy the second but satisfy the third, and they're in third normal form. So like I said, slightly weaker. All right, so we talked about how we could compute a BCNF decomposition of a schema from by using a set of decomposition rules, basically looking for a functional dependency that wasn't in BCNF and then breaking it apart and forming two tables based on that, that put the schema more back into BCNF form. And you keep doing that until every table in the schema is in BCNF effectively. Right, well, third normal form, the algorithm for computing it is quite different. And it's almost more of a synthesis rather than a decomposition. So step one is that you have to compute a minimal cover. So in another video we talked about how to do that. So you're starting from a set of functional dependencies, and you want to work out a schema that involves the attributes from those functional dependencies that satisfies these conditions. So we start from our functional dependencies, we compute a minimal version of those. Step two, very simple. We basically take all of the functional dependencies in the minimal cover and we turn them into tables. So every functional dependency becomes a table in the overall schema. Okay, so remember that our overall schema consists of a whole bunch of sub-schemas. In this case, all of the sub-schemas are based on the functional dependencies in the minimal cover. Now, when we did the minimal cover example, we noticed that we lost one of the attributes on the way through. It didn't appear in any of the functional dependencies in the minimal cover. So we have to check for that as the final step. And if it turns out that some attribute doesn't appear anywhere, then we can't actually form a key for the schema. So we have to add a new table that includes enough attributes to give a key for the entire schema. So if no table has a key, then we add a table that does have a key for the schema. With the overall schema key. So the last two steps are not actually that difficult. The first step of computing the minimal cover, as we saw in the other video, is a little bit more complicated. So that's the property of a 3NF schema. That's the algorithm to get there. Okay, so for an example, let's take the schema that we looked at before, which consisted of this set of attributes. And where did these come from? Well, there's an application domain, and we can identify all of these properties of interest in the application domain. And that becomes our, if you like, giant global schema. And the set of functional dependencies, I'll use the same ones that we had before. A, B determines C. A determines C. Ooh, maybe it's not the same as the one we had before. And doesn't matter. Okay, so this is our schema. Now we can compute a minimal cover. I'm not going to go through all the steps for that. But it ends up being A determines C. Ooh. Okay, hopefully that's not confusing. That's our original set of functional dependencies. This is an equivalent and minimal set of functional dependencies. Okay, the next step, convert all the functional dependencies into tables. Now the other thing that we do at this point is if we've got two functional dependencies that have the same left-hand side, like the two Ds here, we merge them and produce a table, which in some sense is kind of going backwards from what we did in the minimal cover production algorithm. So our schema for all of these attributes has a table AC, and it also has a table DAE. And of course I haven't finished it off because there's clearly something missing. B doesn't appear anywhere. So that's a problem. So we couldn't form a key for the schema without B. So what we need to do in order to get a key, clearly A has to be part of the key because it produces C. D has to be part of a key because it produces E. And B has to be part of the key. So A, B, and D, if we add that as a table, then we've got a schema that incorporates all of the attributes from the original schema, and has the property that it's in third normal form. So that's how you could use this algorithm to start from this schema, this set of functional dependencies, and produce a final schema in third normal form.